Okay, I'm gonna get started because we need to make sure we get through this today. So the chapter 15 homework is due on the 17th. The chapter 15 quiz will be on Wednesday, the 15th. The test grades, they're graded. I just need to finish the curve. And so they'll be up by tonight, later today. And there is a lab today, and your previous lab is due. And please do get me those because midterm grades are due on Wednesday morning. So that previous lab will be on, the volcanic rocks lab will be on the midterm grade. So continuing on, we were talking about latitude and longitude. Latitude is the angular measurement north and south of the equator in degrees north and south of the equator. So we're on a ball. Because we live on a ball, we measure things with angles. So if you look at the angle from the center of the earth as you go up, you go north or south, that is latitude. It's a series of slices through the earth, all parallel to the equator. And it gets, those circles that they form get smaller and smaller as you head towards the poles. Lines of latitude are equally distant from each other. Latitudes are also called parallels. There's an infinite number of them. Going from the equator to the poles, these parallels represent a series of complete circles in which the equator is the largest and they become smaller going north and south. And the point on the other side of the earth will have the same value with the opposite direction. So if you are at 40 degrees north, you go to 40 degrees south. Longitude is sort of rotational. You know, what angle you end up as you rotate around, east and west. These are imaginary lines drawn on the surface of the earth running from the north to the south pole. They're not parallel. They all meet at the poles. They're closer together at the north and south. They're widest at the equator. Lines of longitude are called meridians. An infinite number of lines can be drawn as meridians. Every meridian is a half of a great circle. So longitude is the angular measurement in degrees east or west of a reference meridian, which is the prime meridian. That location is arbitrary. It's in Greenwich, England, because they wanted the big conference, basically. There were a few competing options that was basically boiled down to it was either going to be the English one or the French one. And the Americans were supporting the English, and the French were on the outs with the rest of Europe at the time. And so we ended up with it in Greenwich. There's a maximum value of 180 degrees east or west. Both of those are the same position because it's opposite zero. If you're at a spot on the earth where the longitude is 80 degrees west, the other side of the earth, you would subtract that 80 degrees from 180 degrees to figure out where you are. So 100 degrees east would be opposite 80 degrees west because 180 minus 80 is 100. So if you were at 60 degrees west, the opposite side of the earth from you would be at 120 degrees east. So that's longitude and latitude. Additionally, the earth is divided into time zones for standardized time. This is a relatively recent thing because everybody used to just use local time. But then trains happened, and scheduling trains efficiently so they didn't run into each other required a standard time across the entire system of trains. And then this sort of led to everybody adopting that. There's some even weirder things that have happened with that, where at one point all the French train system was like off by 5 minutes because people were always like complaining about being late because of the difference between local and train time. So train time was set up to be about 5 minutes after standard time, so people weren't late. Nightmare. The Earth is divided into 24 time zones, each containing approximately 15 degrees of longitude or 1 hour. Now, these time zones have been distorted by political decisions, so that they fit with borders or fit with, where people are working. So the lines are not exactly at 15 degrees, every 15 degrees. So the first time zone begins at the prime meridian and extends approximately 7.5 degrees, both east and west. And the centers of each time zone are multiples of 15 degrees. So there's one centered at 0, one at 15, 30, 45, 60, 75, 90, and so on. So for example, in the US, the time zones are nominally centered around 75 degrees west, 90 degrees west, 105 degrees west, and 120 degrees west. But you can see how these aren't really centered in the time zone. This is the 75 degrees west. It's okay. But 90 degrees west for central time, not very centered. And it's even worse for mountain time. Pacific time is maybe a little better. And then there's also Alaska Standard Time, which covers what would be a whole bunch of time zones, but it's just, there's so few people, it's just more convenient to put them all in one time zone. And then Hawaii Aleutian Standard Time. Which, covers Hawaii and a bit of the Aleutian Islands. So Alaska Standard Time is more centered around here, but it's centered around 150. There's not many people over here. So as you travel west, you gain time. So as you cross into a new time zone, your watch will be 1 hour ahead of the new time zone. If you drive from Texas at noon into New Mexico, it's now only 11 a.m. So if you were driving from the eastern half of Indiana to here, you'd go from noon to 11. Driving east, you lose an hour. So if you drive east from here into the rest of Indiana, you will lose an hour. And it'll be an hour later. So right now it is 8:42. In the rest of Indiana, it is 9:42. So if you travel all the way around the Earth going west, you gain 24 hours. You effectively get an extra day out of it. And that was a major plot point in Around the World in 80 Days. If you ever read that book. He succeeded because he went west around the world. And so he saw 80 sunrises and then was a little late, but it turned out 80 days had passed in the UK because he gained a day. So here is a diagram showing the times and dates on Earth for any Tuesday at 10 a.m. Eastern Standard Time. So if it's 10 a.m. Eastern Standard Time, here, it'd be 9 a.m. Central Standard Time. As you head west, you'll eventually hit the international date line. When you cross the international date line, Going west, the date jumps 1 day forward. Going east, the date jumps 1 day backwards. So if it's Tuesday, you'll cross the international date line. It'll be 3 a.m. It'll go from 3 a.m. Tuesday to 3 a.m. Wednesday. If you go east, yeah, it would be 3 p.m. at the Greenwich Meridian. It'd be midnight in Tokyo. And then if you go east, you come the next day, Wednesday, 1 a.m., 2 a.m., and then at the international date line, 3 a.m., kept going east, you jump back to Tuesday at the Greenwich Meridian. So traveling east, the time goes up, but if you cross the date line going east, the date goes backwards. The international date line is located at the 180-degree meridian, exactly opposite the prime meridian. When you cross the international date line traveling west, so in the direction where you'll be going to steadily earlier times, as you cross time zones, the date gets advanced to the next day. So the time zone change and the date line change are in opposite directions. And that means that the whole Earth you can't gain or lose time by going around the Earth somehow. And when you cross the international date line traveling east, 1 day is subtracted from the present day. So here, there's an example of finding the standard time and date in another location. So if it's 6 a.m. on March 21st in Los Angeles, in -8 over here, what is the time and date in Perth, Australia? In +8 over here. So there's two ways we can do this. We can go west or we can go east. Which way would you like to go? Okay, let's go west. We're at -8. We get to Perth, Australia, we gotta go 1, 2, 3. Save 3, 4, 5, 6, 7, 8 to get to Perth, Australia. So that would be 8 hours earlier. So if it's 6 a.m., 8 hours earlier is 10 p.m. on March 20th. But in that process, we cross the international date line going west. So we have to add a day. So it will be 10 p.m. on March 21st. If we go the other way, east, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. We're in Perth, Australia. Keep cutting the bottom. This, we don't cross the international date line, so we just add 16 hours. 16 hours to 6 a.m. 6 plus 16 is 22, but we're over 12, so we subtract 12, we get 10 p.m. And here is a video about how time zones work and the international date line.
In the old days, each town would keep their own times, with a town clock being set to noon when the sun reached its highest point in the sky. However, by the late 19th century, rail had begun to move people across great distances. Schedules became very confusing, as each stop was based on a different town's time. Thus, a need emerged to standardise time so rail could operate more efficiently. In 1884, delegates from 26 countries met in Washington, D.C. to agree on a prime meridian as a common 0 point for longitude. The result was Greenwich, England, being selected as the international standard for 0 degrees longitude and established the 24 time zones. Today, most countries follow the hourly deviations, though they do not always align with longitudes for reasons such as keeping the entire country in one time zone or altering times at certain times of the year, for example, daylight savings time. Time zones are based on the fact that the Earth moves 15 degrees longitude each hour. Since there are 24 hours in a day, there are 24 standard time zones. Time zones are counted from the prime meridian, which is 0 degrees longitude. Each time zone is counted at 15-degree intervals and extends 7.5 degrees either side of the central meridian. For example, Sydney, Australia, lies in the 150 degrees east central meridian, and the time zone includes all locations between 142.5 degrees east and 157.5 degrees east. Now, I will show you how to calculate time zones. First, determine whether the time zone is in the eastern or western hemisphere. If the time zone is east of the prime meridian, such as Australia, it will be at an earlier time than Greenwich Mean Time, or GMT. If it is west of the prime meridian, such as Canada, it will be a later time. Second, count how many time zones away from Greenwich the location is. For example, Greenland is one time zone to the west of Greenwich, so I will subtract 1 hour from GMT to determine the time there. Oslo, in Norway, is one time zone to the east of Greenwich, so I will add just 1 hour to the current Greenwich Mean Time. When counting the number of time zones away a location is, count the time zone your location is in, but do not count the time zone that Greenwich is in. For example, I will count for Buenos Aires, Argentina. 1, 2, 3, 4. So, if the time is 4:34 GMT, I will subtract 4 hours to find out the time for Buenos Aires. The time will be 0:34. The international date line is an imaginary line lying 180 degrees in the line of longitude, on the opposite side of the Earth to the prime meridian. This line separates one calendar day from another. The international date line deviates in places to avoid crossing any land. In 1994, Kiribati shifted the date line 2,000 miles east to keep the entire country in the eastern hemisphere. In 2011, Samoa and Tokelau skipped a day and moved westward to be in the eastern hemisphere so they could have the same date as Australia and New Zealand, their main trading partners.
Yeah, the thing mentioned with China is, and time zones is really brutal. So yes, China, the whole country is one time zone and it should be 5. Not only that, the time zone it is the time zone of Beijing, which is in the eastern edge of the country. So like this end of the country is off by like 5 hours. Really awful. So here's a way you can work that through we talked about. So if we locate Los Angeles, if you go west, you would go for 8 time zones, therefore it'd be 8 hours earlier or 10 p.m. You going to 10 p.m. with Perth one day before, but you cross the international date line, you pick up a day, so it'd still be March 21st. You can go either east or west. Both ways work. Sometimes it's easier to avoid crossing the international date line, so you don't have to think about it. But either way works. Yeah, the China thing is, that's an issue. So during the year, the sun will appear to change its overhead position from 23.5 degrees north to 23.5 degrees south. So the location of the sun in the sky, it's here in the northern hemisphere. In the summer, it's higher in the sky. In the winter, it's lower in the sky. In the northern hemisphere summer, at its peak, the sun will be directly overhead 23.5 degrees north, the Tropic of Cancer. And then at our shortest day of the year, the sun will be directly overhead 23.5 degrees south, the Tropic of Capricorn. These are special days. They're called the solstices because there's a point where the sun changes direction. The one in the summer is called the summer solstice. The one in the winter is called the winter solstice. And they correspond to the longest and shortest day of the year. So as the Earth revolves around the sun, the noon sun will be directly over different latitudes during the year because of the constant 23.5 degree tilt of the Earth with respect to the sun. And so you get 4 special dates. The solstices. There's the summer solstice, which is June 21st or 22nd. There's the winter solstice, which is December 22nd or 23rd. And is in fact the origin of the date for Christmas, because traditionally in the Roman calendar, the solstice was on the 25th, but the calendar drifted and all kinds of issues happened. But those are the solstices. And then there's 2 equinoxes, one in the spring and one in the fall. In the spring, in March, the 20th and the 21st is the vernal equinox or the spring equinox. And September 22nd or 23rd, this year it was the 22nd, is the autumnal equinox or fall equinox. And at the equinoxes, day and night are exactly equal in length. Equal night, equinox. So if we want to it turns out, if you know where the sun should be based on the date, like where it's directly overhead, you can figure out where you are based on the height of the sun. So at 12 noon, the sun is on the observer's meridian and appears at its maximum altitude about the southern horizon. So for all observers north of the sun. So at local noon, the sun will be the highest it is in the sky. And if we want to measure the location of the sun, there's some important locations. The zenith is the position directly above your head, where you'd see if you look straight up. The altitude is the angle measured from the horizon to the sun at noon. That angle, so if you measure the altitude, the angle, the height of the sun above the horizon at noon. And then the zenith angle is the angle from the zenith to the sun at noon. It's the complementary angle of the altitude. So 90 degrees minus the altitude. So you can use the sun to figure out your latitude, because that altitude of the sun will depend on your latitude on Earth. And you can also get your latitude from other things like the North Star, Polaris. And it's actually easier to use the North Star than the sun because you don't have to correct for the day of the year. So if it's June 21st, we know the sun is at 23.5 degrees north, and we measure our altitude to be 50 degrees. Then our zenith angle will be 40 degrees, and our latitude will be our zenith angle plus the angle of the sun. And that'll be 63.5 degrees north. This is what we're going to be doing in the lab today. So the general idea is you figure out your zenith angle and then you add the angle of the sun. The sun is to the the angle the sun is above the north. So all three of these preceding examples have the same mathematical relationship. Latitude is equal to zenith angle plus the number of degrees overhead the sun is in your hemisphere, or minus the number of degrees overhead the sun is in the other hemisphere. The latitude is zenith angle plus number of degrees north or minus number of degrees south for the sun. So a ship's caption measures the noonday sun if you're in the northern hemisphere. If you're in the southern hemisphere, the south and north switch. So a ship's caption measures the noonday sun at an altitude of 30 degrees towards the south on December 22nd. What is the latitude of the ship? So it's December 22nd, it's 30 degrees towards the south. He's in the northern hemisphere. On December 22nd, the sun is overhead 25.5 degrees south. The zenith angle is the complement of 30 degrees. So that's 60 degrees. So zenith angle minus sun degrees, 60 degrees minus 23.5 degrees is 36.5 degrees north. Here's the example. You see 60 degrees because you measured 30, and then you have to add 20, you have to subtract 23.5 degrees because the sun is below the equator. Here, a ship's caption measures the altitude at altitude of 70.5 degrees towards the north on December 22nd. What is the latitude of the ship? So notice here the sun is to the north. So that means you're in the southern hemisphere. So the zenith angle is 19.5 degrees, the complement of 70.5 degrees. The sun is at 23.5 degrees south. So the zenith angle plus the sun degrees, because you're in the same hemisphere. The sun is very high in the sky in our winter. So 19.5 degrees plus 23.5 degrees is 43 degrees south. And in theory, determining longitude would be easier because, the sun travels westward at a steady rate, and we should be easy because the sun travels westward at a steady rate of 15 degrees per hour. And it is easy if you have a clock that was set at a known location that keeps good time. But if you don't, because building one of those is actually really hard, then it actually is really hard to do. So there was this longitude problem. It took them a very long time to get a good way to get longitude. At least the Western people did. The Polynesians had something because the Polynesians were like the best sailors ever. But a lot of that knowledge was lost. So for example, if the noonday sun position in your position is observed at 2 p.m. GMT, then you know you're 2 hours west of Greenwich, or 30 degrees west. So 15 degrees per hour times 2 hours is 30 degrees west. But you need a clock at Greenwich Mean Time. In the modern day, that's easy. We can transmit that time everywhere. We can keep a clock that's stable with you easily. But back in the day, on a ship with mechanical clocks, that was hard because mechanical clocks lost or gained time. They weren't necessarily the most accurate. And being on a ship with its rocking and vibrations was really bad for clocks. So as the Earth revolves around the sun, its axis remains tilted at 23.5 degrees from vertical. And the fact that it is causes the seasons. This constant tilt with respect to the sun causes the Earth's seasons. When the Earth is furthest from the sun, it's in July. It's summer here. It's winter in the southern hemisphere. I mean, the thing about it, it's due to the tilt. One half of the Earth has winter, the other half has summer. The closest point to the sun in the Earth's orbit is in January. You know, not warm in Chicago though. So as the Earth revolves around the sun, there are 4 special days. These are the solstices, the winter solstice and the summer solstice, and the equinoxes, the vernal equinox and the autumnal equinox. So the winter solstice, the vernal equinox, which is the spring equinox, the summer solstice, and the autumnal equinox, which is the one in fall. And light and dark hours are always the same at the equator. So, on March 20th and 21st is the vernal equinox. Then you have the winter solstice, December 22nd or 23rd. Then you have the autumnal equinox, September 22nd or 23rd. Then you have the summer solstice, June 21st and 22nd. And the reason there's an or there and 2 possible days is because the year is not perfectly a round number of days. So it's not always the same day. Because the year is 365.25 days. So, on the winter solstice, the northern hemisphere winter solstice, the sun is above 23.5 degrees south, the Tropic of Capricorn. So there's a lot. The parallel of 23.5 degrees south is called the Tropic of Capricorn, because that's the furthest south the sun can be directly overhead. That's known as the tropics. Then there is the vernal equinox at 0 degrees. That's at the equator. The sun is above the equator. The summer solstice. The sun will be about 23.5 degrees north. That's over the Tropic of Cancer. So at the winter solstice, the sun is lower in the northern hemisphere. There are fewer hours of daylight, and the sunlight is less intense because it's at a shallower angle. We get less heat from the sun because the same light is spread out over a bigger area. And in the summer, the sun is higher in the northern hemisphere. There are more hours of daylight, and the sunlight is more intense. And then at the autumnal equinox, the sun is over the equator. So the autumnal equinox was a little while ago, the 22nd. And we're coming up, we're headed towards the winter solstice. So that will be, you'll be on vacation then, because it's, 20 something December. So the sun's overhead position is never more than 23.5 degrees latitude. It goes between 23.5 degrees north and 23.5 degrees south. The sun's position will always be due south at 12 noon local solar time for an observer in the conterminous US. The solstice is the farthest point of the sun from the equator. It's the name comes from the sun standing still. Solstice, the stis is the still, sol is sun. The summer solstice is when the sun is at its most northern position. The vertical noon sun is at 23.5 degrees north. The winter solstice is when the sun is at its most southern position. The vertical noon sun is at 23.5 degrees south. So the sun's position overhead varies from 23.5 degrees north to 23.5 degrees south of the equator. When it's directly over the equator, both the day and night have 12 hours all over the world, except the north and south poles, which are weird exceptions we don't need to worry about. because nobody lives there. These are called equinoxes because equal night. The sun is directly over the equator. The vernal equinox is March 21st, 20th or 21st. The autumnal equinox is September 22nd and 23rd. It was September 22nd this year. And due to the great distance from the sun, the light rays incident on the Earth's surface are parallel. So one half of the Earth's surface will be illuminated in daylight all the time, and the other half will be in darkness. So, at any one given time, half the Earth is illuminated. But the number of daylight hours at any place on Earth depends on the latitude and the day of the year, because that illumination, the half that's illuminated, doesn't necessarily pass through the axes. So here is a short clip about the seasons showing the variation throughout the year and how the daylight changes.
The axis of the Earth is an imaginary line on which the Earth rotates. It links up the two poles. Both the axis and the Earth are tilted at an angle of 23.5 degrees during a revolution. The tilting of the axis results in direct sunlight falling on different places during different seasons. This causes variations in the duration of days, nights, and seasons. Relationship between the location of the overhead sun and the seasons. Similarly, the revolution of the Earth and the tilting of the axis results in different angle of the sun during different periods. When the sun is directly overhead, we call this the overhead sun. At this time, the Earth's surface and the midday sun forms a 90-degree angle. Different locations of the overhead sun results in variations in the amount of solar radiation received in different areas and at different periods. Spring equinox on the 21st or 22nd of March. The overhead sun is over the equator. The equator receives the largest amount of solar radiation. At this time, the northern hemisphere is in the spring equinox, while the southern hemisphere is in the autumn equinox. The angle of the sun decreases towards the poles. On this day, the two hemispheres receive a similar amount of solar radiation, and the length of day and night is the same at all places on the Earth. After this day, it is spring in the northern hemisphere, where the day is longer than the night. In the southern hemisphere, it becomes autumn, when the day is shorter than the night. Summer solstice. On the 21st or 22nd of June, the overhead sun is over the Tropic of Cancer. It receives the largest amount of solar radiation. At this time, the northern hemisphere is in the summer solstice, while the southern hemisphere is in the winter solstice. The angle of the sun decreases towards the poles. On this day, the length of daytime of the northern hemisphere is the longest in the year, while that of the southern hemisphere is the shortest in the year. Besides, there are 24 hours of daylight at the Arctic Circle and 24 hours of darkness at the Antarctic Circle. Autumn equinox. On the 22nd or 23rd of September, the overhead sun is over the equator again. the equator receives the largest amount of solar radiation. On this day, the northern hemisphere is in the autumn equinox, while the southern hemisphere is in the spring equinox. The angle of the sun decreases towards the poles. On this day, the two hemispheres receive a similar amount of solar radiation, and the length of day and night is the same at all places on the Earth. After this day, it is autumn in the northern hemisphere, where the day is shorter than the night. In the southern hemisphere, it becomes spring, when the day is longer than the night. Winter solstice. On the 21st and 22nd of December, the overhead sun is over the Tropic of Capricorn. It receives the largest amount of solar radiation. On this day, the northern hemisphere is in the winter solstice, while the southern hemisphere is in the summer solstice. The angle of the sun decreases towards the poles. On this day, the length of daytime in the northern hemisphere is the shortest in the year, while that of the southern hemisphere is the longest in the year. There are 24 hours of darkness at the Arctic Circle and 24 hours of daylight at the Antarctic Circle.
So, the circle of illumination is the half of the Earth that's lit up at the equinoxes. The circle of illumination goes from pole to pole and splits the Earth neatly in half, night and day. So everyone has 12 hours of daylight and 12 hours of night. So this is the northern hemisphere summer solstice. You can see the circle of illumination cuts across, but it's not aligned with the axis. So some areas have longer days and shorter nights, and some areas have longer nights and shorter days. And the most extreme example is above the Arctic Circle here, where you have 24 hours of daylight, and below the Antarctic Circle here, where you have 24 hours of darkness. So one other thing the Earth does is that it precesses. So if you spin like a top, you'll notice that it wobbles. So if you spin a top, it spins around its axis, but it sort of wobbles around. I don't have a good example I could show you right here, but that is something that happened. This wobble is called precession. I don't think I have a gyroscope for demos, so I don't have an easy demo for that right now. And the Earth also precesses because it is tilted and it's affected by the gravity from the sun. This actually causes a small amount of precession. And it slowly precesses in a clockwise direction. And the period of this precession is not fast. It takes one complete cycle of wobble takes 25,800 years. Now, interestingly enough, this was discovered like thousands of years ago. It was discovered in 150 BC by Hipparchus, studying the centuries of astronomical data that actually existed then. He was an ancient Greek, but he was studying like Babylonian and other people's astronomical data and putting it together. So in other years, it takes 25,800 years for the axis to precess through 360 degrees. This leads to some amusing things, like the fact that modern zodiac signs are all off with the actual position of the sun in the zodiac. So the dates given for zodiac signs are all off by a bit. Because they're like old. But so as the Earth precesses, Polaris will no longer be the North Star. It will change. Eventually, it will be Vega. And the precession of the Earth axis has minimal influence on the seasons because the tilt of the Earth with respect to the Sun remains the same. It just changes what direction it's pointing in. But it will change which stars can be seen in each hemisphere in each season. But that's the only real effect for it. So here's a short video about the precession of the Earth. The Earth is wobbling slowly.
The Earth's axis points at the North Star, and the heavens have been revolving around that star since the dawn of time. Except they haven't. When the Egyptians built the pyramids, the North Star wasn't our current North Star, Polaris. No, it was Thuban. Why did it change? It's because the Earth's axis is moving. This motion was first discovered by Hipparchus. He was looking at the positions of the stars and comparing them with their positions a century earlier at the same time of year. He found that the stars were moving at least 1 degree every century. What could be causing this motion? When you're riding a car and the car turns, you feel an acceleration. In the same way that you experience an acceleration when a car turns, there is also an acceleration as the world turns.
This acceleration works against the force of gravity. So you actually weigh less at the equator.
And you weigh more when you're at the North Pole. 1% more.
This also causes the Earth to bulge. The Earth is 26 miles wider at the equator.
Because the Earth is not a perfect sphere, the gravitational force of the Sun isn't perfectly balanced. One side of the Earth gets tugged just a little bit more, and this causes the Earth's axis to spin, completing one revolution every 26,000 years. This also affects the length of the year. Now, you can measure the length of a year several different ways. One way is to look at the seasons. This is called the tropical year. Another way is to look at the positions of the stars. This is called the sidereal year. In January, the sun is in the constellation Capricorn, which means children born in January have Capricorn as their astrological sign. Over the course of a year, the sun moves through all the signs of the zodiac. Once the Earth is back in its original location, we have completed one sidereal year. But the tropical year doesn't depend on the Earth's position. It depends on the Earth's axis. When the North Pole faces away from the sun, we in the Northern Hemisphere experience the winter solstice, the shortest day of the year. If you measure the length of time between two winter solstices, you get a tropical year. So, what's different? Well, if the Earth's axis is moving, it could line up with the sun before the Earth has returned to its original location. This is what happens. Although the effect is small, the axis only moves about 1/100th of a degree, and a tropical year is only 20 minutes shorter than a sidereal year. How did this affect the development of the calendar? Let's go back to the Romans. You may remember Julius Caesar as the man who conquered the Gauls, overthrew the Roman Republic, and named the month of July after himself. But in his free time, he cleaned up the Roman calendar, which was a total mess. Before Caesar, the calendar lasted between 355 days and 378 days. Caesar put it at 365 days, with a leap day every 4 years. This was the Western calendar, until Pope Gregory XIII said, That's not good enough. He removes some of the leap days to better match the length of a tropical year. The Gregorian calendar wasn't adopted in Russia until 1918, and as a result, the Russians showed up at the 1908 Olympics 12 days late. Why did Pope Gregory base our calendar off the tropical year? What if he had used the sidereal year?
Imagine it's the year 15,000 AD.
And Americans are celebrating Christmas in the middle of summer, and that is what a sidereal calendar would mean. Now, a tropical calendar gets the seasons right, but it puts the Earth on the opposite side of the sun
In the year 15,000.
And so, Geminis will be born in December, Cancers in January, Leos in February, Virgos in March. Everything will be backwards.
And as we know from astrology, the position of the sun and planets at the moment you were born predicts all future events in your life. Here's a chart showing you the positions of the planets when I was born. As you can see, I am destined for greatness. Don't believe me? Just look at my horoscope today.
Today, you will make a YouTube video. Some people will think that you love astrology, while others will think you're being sarcastic. But everyone will love your video. For more astronomical videos,
So. So. Let's look at the precession of the top and Earth. So if you see a top, it wobbles, you'll see its tip. As it spins, will sort of precess about. A similar thing happens with Earth over a period of about 26,000 years. So in 14,000 CE, the pole star will change from Polaris to Vega. So in some 12,000 years. And the precession of the Earth doesn't really affect us much. We use the tropical calendar because it actually matches the seasons. It matches the position of the sun in the sky, which is important for getting Easter right, which is why the Gregorian calendar is the way it is. It's all about getting Easter right at some level. But it is a more accurate and better calendar. But yes, people argued over and fought against using it for literally hundreds of years. That is the end of chapter 15. So another name for the parallel lines on the Earth's grid system are they are lines of latitude, like a ladder. Another name for the meridian lines of the Earth's grid system are lines of longitude. They go along as you travel along. Of these lines, the ones that are equidistant from each other are the parallels, the lines of latitude. All meridians intersect at the poles, the North and South Pole. The maximum value of the parallels is 90 degrees north and 90 degrees south. The maximum value of the meridians is 180 degrees east and 180 degrees west. Lines of latitude are measured north and south of the equator. Lines of longitude are measured east and west of the prime meridian. The approximate latitude and longitude of Spain, well, this is Spain. So latitude, it's 40 degrees. Longitude, I don't know, I would say 40 degrees north, maybe 5 degrees west. It's just a little bit west of 0. One type of map keeps both latitude and longitude lines parallel, but in doing so, distorts landmass sizes. That's the Mercator projection. What type of map shows the features of the ocean floor? That is a bathymetric map. The type of map that shows land elevations is a topographic map or a contour map. The type of map that attempts to remove landmass size distortions is the Peters projection. The type of map that shows the type of rocks found in an area is a geological map. The difference between two contour lines is called the contour index. Tightly packed contour lines tell you that the slope in that area is steep. Widely spaced contour lines tell you that the slope in that area is gradual. Hatcher lines on our contour map indicate which way is down. They point down slope. Gradient indicates the steepness of the slope. It's determined by dividing the change in altitude over the distance. What is longer, the sidereal day or the solar day? The solar day is about 4 minutes longer. How many degrees does the Earth complete its orbit around the sun in 1 day? In a sidereal day, 360. In a solar day, 361. How many time zones are there? 24. How many degrees of longitude separate each time zone? 15. If there's 15 degrees, 360 degrees divided by 15. Divided by 24 gives you 15. If you travel west, you will go to an earlier time, so you will gain an hour of time. If you travel east, you will go to a later time, so you will lose an hour of time. The prime meridian is located at 0 degrees longitude, while the international date line is located at 180 degrees longitude. The latitude line located at 25.5 degrees north is called the Tropic of Cancer. The latitude line located at 23.5 degrees south is called the Tropic of Capricorn. And to calculate your zenith angle, one would subtract the altitude of the sun from 90 degrees. To calculate your longitude from sun position data, one would multiply the number of hours difference for the noonday sun from GMT time by 15 degrees. And seasons on Earth are due to the tilt of the Earth's axis. And when the direct rays of the sun reach 23.5 degrees north or south, the days these occur on are referred to as the summer and winter solstices. When the direct rays of the sun are at the equator, the days these occur on are referred to as the vernal and autumnal equinoxes. Due to the circle of illumination, the poles have exactly 6 months of day and night. And the Earth's axis actually moves in a predictable pattern every 26,000 years. This is referred to as the precession of the Earth's axis. Let me just show you something. Come on. So just announcements. Chapter 15 homework is due on the 17th. The Chapter 15 quiz will be on the 15th Wednesday. The test grades will be posted to Blackboard later today. I'm just finalizing the curve. And the next thing we're starting is chapter 19. And this, you know what? I think, well, we could start chapter 19 today. I think I'll just start it on Wednesday. We only have like 10 minutes left, so. Actually, maybe I'll start a little and then I can go a little quicker on Wednesday. Enable. So for the atmosphere, we'll go over the four main gaseous constituents of the atmosphere and give their percentage of abundance. We'll describe the divisions of the atmosphere based on temperature, which are the troposphere, stratosphere, mesosphere, and thermosphere. We'll describe the properties and functions of ozone in the atmosphere. We'll describe the processes of ozone production and depletion in the atmosphere. We'll look at the distribution of insolation on the Earth from the sun. We'll discuss the greenhouse effect. We'll discuss latent heat of evaporation and condensation and how that affects the atmosphere. We'll describe the process of heat conduction on the Earth's surface and describe how the temperature of the atmosphere varies with altitude. We'll talk about what's meant by air pressure and how it's measured with a barometer. We'll name and describe the fundamental atmospheric pressure measurements essential to determine overall weather conditions, which are temperature, pressure, humidity, wind speed and direction, and precipitation. We'll talk about the difference between absolute humidity and relative humidity. We'll talk about the data that goes into the heat index. We'll describe what a dew point is and how it relates to precipitation. We'll describe how a psychrometer measures relative humidity. We'll go over using psychrometer tables, how to calculate the relative humidity, maximum moisture content, actual moisture content, and dew point. We'll describe what causes wind and air currents. We'll describe isobars and describe the general movement of air between different isobars. We'll describe the formation of sea and land breezes. And we'll describe the Coriolis force and how it affects the rotation of winds in the northern hemisphere. We'll differentiate between cyclones and anticyclones, describe jet streams, and describe the differences among the four cloud types, cirrus, cumulus, stratus, and nimbus, and describe how clouds form. So the atmosphere is the shell of gas or air that surrounds the Earth. So here's sort of an introductory video to the atmosphere.
Funny. The man has jokes.
He's funny. Okay.
Okay.
So meteorology is commonly applied to the study of, is a term that's commonly applied to the study of the lower atmosphere. In the past, it was used to more generally describe the study of the entire atmosphere, hence why meteor and meteorology have the same root. It was stuff overhead. And the conditions of the lower atmosphere will be called the weather. So in this chapter, we'll examine the atmosphere's composition, properties, and mechanisms. And look at its nature. So the atmosphere, our atmosphere is composed of a mixture of gases, and it holds various amounts of suspended liquid droplets and solid particles. Not about 99% of the by volume of air near the Earth is made up of two gases, nitrogen and oxygen. And both of these dominant gases, they're diatomic. They consist of two atoms forming a molecule, N2 and O2. And next we have argon, which makes up about 0.9%, just a little under 1% of the atmosphere. And then carbon dioxide, which is 0.03% on the other major constituents of air. That is inching up towards 0.04% on carbon dioxide, unfortunately. And then there's small quantities of other gases found in the atmosphere. And this is dry air, because the amount of water vapor in the air varies drastically. So this is sort of on average, or just if you have dry air. So dry air is composed primarily of two constituents, nitrogen, 98%, oxygen, 21%. And then we have argon, 0.9%, carbon dioxide, 0.03%. The size is exaggerated so you can actually see it. And everything else in the atmosphere is much smaller quantities. So other trace things, we have neon, helium, methane, nitrous oxide, hydrogen. But there are some other things that have variable amounts. Water vapor has the biggest variation. You could have from 0 to 4% in the atmosphere, in the air, depending on conditions. Carbon monoxide, you would like to have as little as possible. Ammonia, also you would like to have as little as possible. And then things like solid particles, dust, pollen, etc. And we're out of time for today, so we'll go over this again on Wednesday. But we can probably skip the video. So I'm gonna stop sharing and